In this exercise, we will illustrate how we can solve a constraint optimization by using the Lagrange functions. In this case, we want to optimize the function f subject to the following linear equation. Notice that in this particular case, we want to find the optimal x and y that maximizes the function. And then we need to calculate the optimal value for the function. Notice that in this particular chapter, we will only focus on the first order conditions. We will not evaluate the maximization or the minimization requirement. This will be done in future chapters. So let's start by finding the optimal x and y that maximizes the function, and then we will move to find the optimal value for the function f. To solve this constraint optimization, we need to recognize that here the f function is our objective function, and then the restriction here is the linear constraint. But in order to use it, we need to move the left-hand side to the right. So this is going to be 0 equals 28 minus 4x minus 5y. So this is going to be the way that we will need to write our restriction. So remember, we normally will have 0 in one of the sides, normally in the left-hand side. So this is going to be our restriction. Then we will need to define the Lagrange function. And notice the Lagrange function is equals to the objective minus lambda times the restriction. But remember, the restriction must be equals to 0. So in this form, you need to have it before you implement it in the Lagrange function. In this case, the Lagrange function is a function of x and y, which are the original two variables, and also lambda, which is a new variable that we inserted here. So this is equals to the objective function here is 2x squared y to the fifth minus lambda times the restriction. In this case, this is 28 minus 4x minus 5y. Notice something interesting. This is like subtracting a value of 0 because, as you can see here, 28 minus 4x minus 5y is simply 0. So in other words, optimizing the Lagrange function is the same as optimizing the objective function. And then we proceed with the first order conditions. Here we have three partials. First, with respect to x. So here we have 2y to the fifth is the constant part times the derivative of x squared, which is 2x, minus lambda times, inside these parentheses, the only part that has x is minus 4x. So minus 4 times the derivative of x with respect to x is 1. And we set that equals to 0. Now let's pass to the partial of the Lagrange with respect to y. Notice that here 2x squared is the constant part times 5y to the fourth, which is the derivative of y to the fifth, minus lambda times, inside this parentheses, the only part that has y is minus 5y. And the derivative of minus 5y with respect to y is simply minus 5 times 1. And the reason why I can't do that is because the lambda is multiplying, so it really doesn't make any difference. Because the variables that we are taking the derivative are actually inside the parentheses. And then this we set also equals to 0. And finally, we need the third variable. So the derivative of the Lagrange with respect to the lambda. Notice that in this first case, the objective doesn't have lambda, so this is 0. And then between these factors, the only part that has lambda is in the first part. So the derivative of lambda with respect to lambda is 1 times everything that it was multiplying. So this is 28 minus 4x minus 5y. The only reason why we can do that is because if you try to use a product rule, the only place that actually we can use it is on the left, because on the right there is no lambda. And now we can formulate it as normal equations. Notice, for example, here, this is 2 times 2 is 4, x, y to the fifth, and here, this is minus 4 times 1 is minus 4, times minus lambda is plus 4 lambda, but we're going to move it to the right hand side. So this is equals to the minus 4 lambda. Here we have 2 times 5 is 10 x squared y to the fourth. Again, minus 5 times 1 is minus 5 times minus lambda is plus 5 lambda. If we move it to the right hand side, this becomes minus 5 lambda. And finally here, we can multiply everything by minus 1. So we are going to obtain 28 minus 4x minus 5y equals 0. And as you can see, always in the Lagrange with respect to lambda, you will always obtain the restriction again. So in that way, you can verify your answer. Now let's copy these two on the next page. Notice that we have 3 equations and 3 unknowns, therefore we can solve this problem. But we cannot use the Kramer's rule because these 3 equations are nonlinear, specifically these 2. But what we can do here is let's divide the first equation by the second equation. So as you can see here, if we divide this one and this one, so 4 divided by 10, so let's write it here together, and minus 4 lambda, and then we will divide by the second equation. Notice something. First, one advantage here is that the lambdas cancel. And then we have to be careful here. Notice, here we have x1, and then this 2 goes up with a negative sign. The same for y. The numerator has an exponent of 5, but then the denominator has y to the fourth, so we can move the exponent up, but because this is a fraction and the exponent is in the denominator, we move it up with a negative sign. And then the constants, what we can do is move it to the other side. For example, here we have -4 and -5, right? So here we're going to move the 10, we'll move it to the next, to the other side of the equation. So this is going to be 10, and then the fourth goes down. So we are multiplying, in other words, every side by 10, and we are multiplying every denominator of both sides by 4. So here we cancel this, and then we obtain on the right hand side this. Now you will notice something interesting. Here the negative and negative disappears. Then 4 and 4 disappears. And 10 divided by 5 is 2. And then this is x to the -1, and this is y to the 1 equals to 2. So as you can see, all these fractions were simplified to this. And this we can move it as y over x. So this is equals to 2. In other words, the optimal relationship that we will obtain is y equals to 2x. This relationship obtained from the first and second equation, we will use it in the third equation. So we will always use that relationship in the restriction. So let's use it here. So here we have that 28 minus 4x minus 5y. But instead of y is equals to 2x. So this relationship that we obtained here, we're applying. So y is equals to 2x. And this is equals to 0. So notice that here we're going to have 28 minus 4x minus 10x equals to 0. 28 minus 14x is equals to 0. This means that x is equals to 2. If x is equals to 2, this means that y is equals to 2 times 2, which is 4. So this means that we found the optimal values for x and y. And finally, the question is, what is the optimal value for the function? And this is simply the function in which we insert the optimal values for x and y. So the function was 2x squared y to the fifth. So here we're going to have, when we replace with x equals 2 and y equals to 4, let's see what happens. So this is going to be 2 times, instead of x, we're going to write 2, and this is a square, times, instead of y, we will write 4. And this is to the fifth. This means that the optimal value for the function at 2, 4 is equals to 8192. So this is the optimal value.